everyone, welcome back to Math with Arya. Today, we are going to be learning how to graph rational functions. Rational functions are functions that can be written as a polynomial divided by a polynomial. There are two types of rational functions. The first one is a reciprocal function which is represented by a constant over a polynomial, and the second type is a common rational function which is a polynomial over another polynomial. In both cases, the denominator cannot equal to 0. In order to graph a rational function, it's really important to understand the key characteristics of the function. So let's start by talking about the discontinuities. Discontinuities happen when f of x is undefined, which occurs when the denominator equals to 0. The two types of discontinuities in rational functions are removable discontinuities, which are holes, and infinite discontinuities, which are horizontal, vertical, and oblique asymptotes. So let's start by taking a look at removable discontinuities. These holes occur at x equals 0 if a is a 0 for a factor that is in the numerator and the denominator. For example, in the function provided, if we take a look at its factored form, we can see that x equals 3 is a 0 for the factor x minus 3, which is in both the numerator and the denominator. Therefore, there is a hole at x equals 3. To find the exact coordinate of this hole, we have to plug in the x value to the simplified equation to solve for y. After doing so, as you can see here in the graph, you would draw a hole at the point 3, negative 1.5. So now let's take a look at horizontal asymptotes. There are three distinct outcomes when checking for these asymptotes. Case 1 is, if the degree of the denominator equals the degree of the numerator, there is a horizontal asymptote at y equals a over b. A is the leading coefficient of p of x, and b is the leading coefficient of q of x. Case 2 is, if the degree of the denominator is greater than the degree of the numerator, there is a horizontal asymptote at y equals 0. Case 3 is, if the degree of the denominator is less than the degree of the numerator, there is no horizontal asymptote. To test yourself, check the examples below and ensure you understand these three cases. After determining the horizontal asymptote, we have to determine the actual graph behavior at this asymptote. As x approaches positive infinity or negative infinity, the function can approach the horizontal asymptote from above it or below it. The horizontal asymptote can also be crossed. So to determine if the function is approaching the horizontal asymptote from above or below, plug in a very large and a very small value of x to the rational function and solve for y. Then use the result of y to determine if the function is approaching the asymptote from above or below. You can use the example below to check your understanding. Now, to check if the function will ever cross the horizontal asymptote, say at y equals p, set the rational function equal to p. If there is a real value of x, the function crosses the horizontal asymptote at point x, p. You can see the example below in equation and graph form where the function crosses the asymptote y equals 0. Now let's talk about vertical asymptotes. If you pause the video and look at the example provided, you can see that these asymptotes can simply be found by finding the zeros of the factors in the denominator that are not common to the factors in the numerator. With regards to the graph behavior, as the function approaches the vertical asymptote from the right or the left, the function can approach positive or negative infinity. And unlike horizontal asymptotes, vertical asymptotes cannot be crossed. So to determine the behavior of the vertical asymptote, plug in a value of x that is slightly smaller and slightly larger than the vertical asymptote, and solve for y. Following along with the example, use the sign of the y value to determine if the function is approaching positive or negative infinity on each side of the asymptote. Another detail that is important is that the degree of the factors which determine the vertical asymptote affects the behavior at the asymptote. If the degree of the factor in the denominator is odd, on each side of the vertical asymptote, the function will approach infinity in opposite directions. However, if the degree of the factor in the denominator is even, on both sides of the vertical asymptote, the function will approach infinity in the same direction. Finally, we have oblique asymptotes. These asymptotes happen if the degree of the denominator is 1 less than the degree of the numerator. An example is provided to show that the equation of the oblique asymptote is simply found by using long division to solve for the equation of the rational function. With regards to the graph behavior at the oblique asymptote, the same method as with the horizontal asymptote can be used to determine if the graph approaches the asymptote from above or below, as well as to see if the function crosses the oblique asymptote. Please be sure to pause the video if you would like to check the examples to ensure your understanding. The next characteristics that help us graph rational functions are the intercepts. The x-intercepts are simply the zeros of the numerator after the common factors in the numerator and denominator have been cancelled out. The y-intercept is the y value when x is 0, which will always be the ratio of the constant terms in the numerator and the denominator. Finally, to find the turning points and points of inflection of a function, find the equation for the instantaneous rate of change at any x value. Once you have an equation, set the IROC equal to 0 and solve for x. Plug these values of x into the rational function and solve for y to find the exact coordinates. Determine if these points are turning points or points of inflection by plugging in values of x that are slightly bigger and slightly smaller than the x values with IROC 0. Solve for y and then use these points to determine the behavior of the graph around the point with IROC 0. You will then be able to tell if it's a turning point or a point of inflection. So now that you know how to analyze the characteristics of a rational function when given its equation, it's really helpful to follow these steps when graphing the function. With that being said, let's try to graph this function. So the first step is to find the y-intercept. The constant term in the numerator is negative 48 and in the denominator is negative 12. Negative 48 over negative 12 is equal to 4, so the y-intercept is 0, 4. The next step is to factor the function. If you would like to pause the video, you can see the detailed process of using factor theorem and synthetic division to factor the numerator and denominator. At the bottom right is the final factored equation. With this equation, we can now determine the discontinuities and x-intercepts. Since there are no common factors in the numerator and denominator, there are no holes. So let's take a look at the denominator for the vertical asymptotes. There are two factors that can be set to 0. For x minus 1, x equals 1 is a 0, and for x plus 3, x equals negative 3 is a 0. For x squared plus 4, there is no value of x that will make this factor equal to 0. Therefore, there are two vertical asymptotes at x equals 1 and x equals negative 3. Taking a look at the numerator now, we can see that there are three factors that can be set to 0. X plus 2, x minus 3, and x minus 4. The zeros of these factors are negative 2, 3, and 4, representing the three x-intercepts. X squared plus 1 cannot be set to 0, and therefore it does not represent an x-intercept. Moving on, we can see that the degree of the numerator, which is 5, is 1 more than the degree of the denominator, which is 4. Therefore, there is no oblique asymptote. If you pause the video, you can see the long division that was used to find the equation of this oblique asymptote, which is y equals negative 2x plus 14. Now to check if the function crosses the line y equals negative 2x plus 14, we set the rational function equal to negative 2x plus 14. By using cross multiplication, we solve for one real value of x. Plugging this value into negative 2x plus 14, we can see that the function crosses the asymptote at point 0.708, 12.58. Now let's take a look at the behavior at the oblique asymptote as x approaches positive infinity. For a large value of x, I substituted 1000 into the oblique asymptote equation with the remainder. When x is 1000, the remainder part of the equation is less than 0. Since this value is less than 0, we are taking away from negative 2x plus 14, which means f of x will be smaller than negative 2x plus 14. Therefore, as x approaches positive infinity, y approaches the oblique asymptote from below. To determine the graph behavior as x approaches negative infinity, I substituted negative 1000 into the same equation. When x is negative 1000, the remainder part of the equation is greater than 0. Since this value is greater than 0, we are adding to negative 2x plus 14, which means f of x will be greater than negative 2x plus 14. Therefore, as x approaches negative infinity, y approaches the oblique asymptote from above. Now let's take a look at the behavior at the two vertical asymptotes. Starting with x equals 1, as x approaches 1 from the left, I substituted 0.99 for x. F of 0.99 is approximately 360. This is a large positive number, indicating that as x approaches 1 from the left, y approaches positive infinity. To check the behavior as x approaches 1 from the right, I substituted 1.01 for x. F of 1.01 is approximately negative 359. This is a negative number, indicating that as x approaches 1 from the right, y approaches negative infinity. For the vertical asymptote at x equals negative 3, I did the exact same process. Substituting negative 3.01 and negative 2.99 for x, the results of f of x show that as x approaches negative 3 from the left, y approaches positive infinity, and as x approaches negative 3 from the right, y approaches negative infinity. Finally, using an online derivative calculator for the IROC equation, then an online calculator to find the value of x when IROC is 0, Then, plugging in x to the equation and solving for f of x, we have determined 4 points where IROC is 0. On the right-hand side, you can see that for all 4 of these points, moving left to right as x moves towards the point, the y value moves in one direction, then reaches the point and begins to move in the opposite direction. Because of this, we know that these points are turning points, and we also know the graph behavior at these points due to how the y value moves. Alright, so now let's take a look at how we can actually use the characteristics of the function to plot it on the graph. So we have all of our important characteristics. We have our intercepts plotted on the graph, we have our turning points which are also plotted on the graph, and we have arrows near the asymptotes to represent the graph behavior at the oblique and vertical asymptote. So let's take a look here. We have a turning point here, we have an arrow here and here. So if we connect all dots together and arrows, we can see that the graph will go here, all the way up there. Now let's come down here. So we have a x-intercept at -2, a y-intercept at 4, and a few turning points and our arrows. So connecting all this together, we can start up here. We have to come all the way down. We have to cross the y-intercept here, and then we're going to reach our first turning point. We're going to turn back up because it's a turning point. We reach our next turning point, we're going to turn back down, and then we cross our x-intercept and we follow the pattern and go down to our vertical asymptote at x equals -3. So now you can see this is our graph in the middle section of the graph. So now let's come to this part. We see we have one turning point here, 2 x-intercepts, and our arrows representing the behavior near the asymptotes. So like we did for the other two, let's connect it all together. We can start at the bottom down here. We're going to come all the way up. We're going to hit the x-intercept, we're going to reach the turning point, and then because it's a turning point, we're going to bring it back down the other way. Hit the x-intercept again, and then connect it to the arrow. So this is how we have demonstrated how we can use the characteristics of a rational function, plot all the important points and the important behaviors of the graph, and here is our rough sketch of this function. Looking at the graph with all key points and asymptotes labeled, we can see that due to the 2 vertical asymptotes, the domain of the function is x is an element of all real numbers but cannot be equal to -3 or 1. Because of the slant asymptote, there are no restrictions on the range. It is an element of all real numbers. For the intervals of increase, we can visually see the parts of the graph that increase from left to right. For the intervals of decrease, we can visually see the parts of the graph that decrease from left to right. To note the intervals where f of x is greater than 0, we simply just look at the parts of the graph that are above the x-axis. And to note the intervals where f of x is less than 0, we look at the parts of the graph that are below the x-axis. When writing these intervals, they always pertain to the x values, and as you can see, there are circled brackets for all of these intervals because both endpoints are excluded in the interval. Alright, let's just try one more example to really solidify our understanding. So the constant term in the numerator is -6, and then the denominator is -8. -6 over -8 is equal to 3 over 4, so the y-intercept is 0, 3 over 4. If you would like to pause the video, you can see the same process of using factor theorem and synthetic division to factor the numerator and denominator, and at the bottom right is the final factored equation. With this factored equation, we can see a common factor of x minus 2 in the numerator and denominator. The 0 of this factor is x equals 2. Plugging 2 for x into the equation, we can see that f of x is 15 over 16. Therefore, there is a hole at this point. Now let's take a look at the denominator for the vertical asymptotes. After canceling out the common factor, we can see the 0 of x plus 2 squared is -2, and the 0 of x minus 1 squared is 1. Therefore, there are 2 vertical asymptotes at x equals -2 and 1. We can also see that there is a horizontal asymptote at y equals 0 because the degree of the numerator, which is 3, is less than the degree of the denominator, which is 5. Taking a look at the numerator now, we can see that the x-intercepts are -3 and -1 from the zeros of the factors x plus 3 and x plus 1. Now let's take a look at the horizontal asymptote y equals 0 and check if the function crosses it. Setting the function equal to 0, we solve 2 values of x, which are -3 and -1. These are the x-intercepts, which makes perfect sense because x-intercepts occur when y is equal to 0, which is the horizontal asymptote. Now let's check the behavior at the horizontal asymptote as x approaches positive infinity. To do so, I substituted 100 for x. F of 100 is approximately 0.0001, which means that as x approaches positive infinity, y approaches the horizontal asymptote from above. To check the graph behavior as x approaches negative infinity, I substituted negative 100 for x. F of negative 100 is approximately 0.00009, which means that as x approaches negative infinity, y approaches the horizontal asymptote from above. Given the function crosses the horizontal asymptote, it makes sense that the function approaches the horizontal asymptote from above as x approaches both positive and negative infinity. Moving on, let's check the behavior at the two vertical asymptotes. Starting with x equals negative 2, for x approaching negative 2 from the left, I substituted negative 2.01 for x. F of negative 2.01 is approximately negative 1103. This is a negative number indicating that as x approaches negative 2 from the left, y approaches negative infinity. Since this vertical asymptote from the factor x plus 2 squared has an even degree of 2, y approaches negative infinity on both sides of the vertical asymptote x equals negative 2. For the vertical asymptote at x equals 1, it's the exact same process. To see the graph behavior as x approaches 1 from the left, I substituted 0.99 for x. F of 0.99 is approximately 8,881. This is a large positive number, which means that as x approaches 1 from the left, y approaches positive infinity. Just like the asymptote at x equals negative 2, this vertical asymptote from the factor x minus 1 squared has an even degree of 2 as well, which means that y approaches positive infinity on both sides of the vertical asymptote. Finally, using an online derivative calculator for the IROC equation, then an online calculator to find the value of x when IROC is 0, then plugging x into the equation and solving for f of x, we have determined one point where the IROC is 0. You can see that for this point, moving left to right, as x moves towards the point, the y value increases, and then it reaches the point and begins to decrease. Because of this, we know that negative 3.893, 0.0301 is in fact a turning point. And now it's time to graph. We're going to follow the exact same process. So first we have all of our characteristics. We have our x and y intercepts, our removable hole, the two asymptotes and their behavior, and one turning point. So now if we move on to this graph, we can see we have all of our points plotted, the hole and the arrows to represent the behavior at the asymptotes. So really all we have to do is connect the dots to the arrows. So if we start over here, we can see that the graph increases until it hits the turning point and then starts to decrease, hits the x-intercept, and goes down to this arrow. So now let's move on to the middle part of the graph. We have an arrow for asymptote behavior here and a y-intercept here. So we're going to connect those. Then we have an x-intercept that we will connect. And from here, we just bring it down to this arrow, representing another asymptote behavior. Now let's move on to the far right side of the graph. All we have is one arrow for asymptote behavior, a hole, and another arrow for asymptote behavior. So all we have to do is connect them together. And there you have it. There is our graphed function. Looking at the graph with all key points and asymptotes labeled, we can see that due to the two vertical asymptotes and one hole, the domain of the function is x is an element of all real numbers but cannot equal to negative 2, 1, or 2. Because the function crosses the horizontal asymptote, the range is not affected by that. However, because of the hole, y is an element of all real numbers but cannot equal to 0.9375. For the intervals of increase, we can visually see that the function is increasing left to right from negative infinity to negative 3.893 and from negative 2 to 1. For the intervals of decrease, we can see that the function is decreasing left to right from negative 3.893 to negative 2, then from 1 to 2 where it reaches the hole, and from 2 to positive infinity. For the intervals where f of x is greater than 0, we can see that from negative infinity to negative 3, then from negative 1 to the asymptote at x equals 1, then from 1 to the hole at x equals 2, then from 2 to positive infinity, the function is above the x-axis. For the intervals where f of x is less than 0, we can see that from negative 3 to negative 2, then negative 2 to negative 1, the function is below the x-axis. These are the final two rational functions that we graphed. I hope this video helped, and if you have any questions at all, please feel free to contact me.